Hello everyone. In the last video, we have seen the proof of lemma 3 and we have also seen the definitions of some of the terms like continuity of a functional, and we defined norm 0, norm 1, norm 2, in general norm n. Okay, the symbol used for the norm was this norm of 1, 0, 1, 2 in general for n. Okay, and we have also defined the quantity distance between the two functions, and the distance between the two functions was also defined for nth order proximity. Okay, that means we have also defined the distance for by taking into consideration the closeness of this. Okay, and yes, so that was it. And now we shall define the admissible curves. Okay, now what is this admissible curve? It's a class of curves where the set of curves satisfying the constraints of the given functional of the given, we will be dealing with variational problems of the given variational problem are called as admissible curves. Okay, and for the simple variational problems, that we will be dealing with, okay, these admissible curves will be nothing but the smooth plane curves. Will be smooth plane curves. Okay, now what do you mean by smooth? Smooth means continuously differentiable. That means the curve will be continuous, then it will be differentiable, and the derivative will also be continuous. Okay, so for the variational problems that we will be dealing with, the admissible curves will actually come out to be the smooth plane curves. Okay, now the set of curves satisfying the constraints of the given variational problem are called as admissible curves. What are these constraints of the variational problem? Okay, so we will be dealing with the problems of the form Vy of x integral from a to b f of x y y dash dx, y at a is equal to y1 and y at b is equal to y2. Okay, so the curves, all those curves which satisfy these constraints will be called as the admissible curves. Okay, if I consider this functional and then if I talk about the admissible curves, then it will be those curves which are satisfying the constraints. Okay, so basically what will happen is it will be something of this form. See, at point A it should be here, no, and at point B, okay, all the curves will satisfy the same condition, otherwise they will go anywhere, but at that point they will satisfy the same condition. Okay, so curves at this point it will be satisfying this condition at this point here, and otherwise they may roam anywhere and come. Okay, but at the end points the constraints will be satisfied by those curves will be the same ones. Okay, so that is the definition of admissible curves. Okay, next we shall define some of the variation or in functional. Okay, before going for the variation in functional, we will have to see what is increment in function and how we can relate that to define the increment in a functional. Okay, so increment in function or increment of function f of x. Okay, increment of function f of x is given by delta f equal to f of x plus delta x minus f at x. Okay, is it very clear from the definition that why it is called as the increment? See, x is the argument of the function f of x. To x we have added some value, we have increased the value of x. Okay, and at that point we have evaluated the function f, and this is function f is evaluated at the point x. Okay, and this difference is called as the increment. Okay, that means the change from this original value, okay, is given by this. If it is this, then what will be the we shall also define accordingly increment of a functional. Increment of a functional. So this increment of a functional, how it will be given? What we have to do is take the original functional at the argument y of x. Okay, then make some change in y of x. Okay, and for that changed value of y of x, evaluate the vy of x. Okay, so that will be delta v equal to v y of x plus this delta y minus v y of x. Okay, now I have taken the original argument of v y of x, v, that is y of x, and then for a small change in this argument y of x, how will the small change in y of x look like? Y of x plus delta y of x. Okay, and at this point the v is evaluated. Okay, so this change is referred to as the increment. Now what is this delta y? Delta y we have already defined before. Okay, so it is the variation in the two functions. Okay, notice that in this case the argument is a point, but in this case the argument of v is not a point, it is a function. So when I talk here about changing the argument, okay, we have added to the point x, we have added some quantity. Okay, means some change is done there. Okay, here what we will have to do is we will have to talk about the variation in the increment in the argument y of x, that is this function y of x. Okay, and I think I have defined it as it was defined as the increment or variation of the argument y of x of a functional vy of x. Okay, so that way this delta y was defined. Okay, so this will give us the increment in the functional. Okay, Next, we will also define the variation of a functional v(y) of x. Okay, the variation of a functional v(y) of x, it is denoted as this. Okay, delta of v, and this delta of v, it actually comes out to be equal to partially differentiating with respect to alpha y of x plus alpha delta y evaluated at alpha equal to 0. Okay, once I start proving the theorem or deriving the condition, you will understand why this variation, that means this quantity, is defined to be like this. Okay, so now what is this variation of a functional? Okay, so first let us relate this and this. Okay, when I say increment of a function f of x is given by this, it can be written in this form. Okay, where delta f is equal to a of x into delta x plus beta of x comma delta x into delta x. Okay, and here this a of x is completely independent of delta of x. Okay, I will not go into the reasoning of why we can write this in this form. Okay, in fact this is the direct, it is going towards proving that derivative of a functional is a linear transformation. Okay, and this you all will study in one of your papers, maybe in next third semester. Yes, okay, so I will not go into detail why we can write it in this form and then how this expression gives rise to the derivative. Okay, and accordingly when we are talking about the derivative, no, here it gives rise to the variation. Okay, and this part, so accordingly how we have written delta of f, delta of v can also be written in this form. Okay, and the things are, this L y of x delta y is a functional that is linear with respect to delta y. Okay, and maximum of this mod delta y is the maximum value of this, the variation in y. Okay, which we have seen. The maximum value of this quantity is this, that is maximum delta y. And this quantity, it goes to 0 as this goes to 0. Okay, and if this happens, that means as this delta y is going to 0, then if this goes to 0, and further to that, if this is a linear part of the functional, okay, then in this quantity what we say is the part of the increment. Okay, so this is the increment, no, the part of the increment of the functional that is linear with respect to delta y, with respect to, sorry, not delta y, in this case it should be delta x, no, yeah, sorry, it should be correct, it should be linear with respect to delta y. That part is called as the variation of the functional, and in this expression the part which is linear with respect to delta y is this part, and therefore this is called as the variation of the functional. Okay, So I will not go in detail why we are writing it like this and what all those things, that delta y going to 0, as this goes to 0, why this is going to 0. It is all taking us towards the finding derivative of this, okay, and as well as this, the differential. Okay, so I will not go deep into that as we don't need it. I just need this quantity because I want to define the extremum of a functional. Okay. In this topic, our aim is to find the extremum of this functional. Okay, extremum means what? It can be either the maximum or the minimum. Okay, when I have given you all the examples of different functionals, okay, and as well as the variational problems, you have seen that we were trying to either maximize or minimize. Okay, like for the Brachistochrone problem, what we wanted to do, we wanted to minimize the time. Okay, so time functional whatever we were getting, we wanted to minimize it. Then for the uh, uh, isoperimetric problem, wherein we wanted to cover the maximum area if given a string of length L, uh, um, we wanted to find a closed curve in such a way that it will cover the maximum area. Okay, so whatever area functional we were getting, actually it is not called area functional, but for your understanding I am saying area functional. Whatever functional we were getting, it was giving us the area, and that we were trying to maximize it. Okay, so when I say extremum, it can be minimum or the maximum. Okay, so now let us actually define or see what does this extremum means. Okay, minimum or maximum. A functional vy of x reaches maximum on a curve y equal to y naught of x if the values of the functional vy of x on any curve close to y equal to y naught of x do not exceed v y naught of x. Okay, that is delta v, where delta v is given by vy of x minus v at y naught of x. This quantity is always less than or equal to 0. If this happens, then we say that v at y equal to y naught of x the curve and the functional v attains the maximum. Okay, and from where this y of x is taken, it is the all those y of x which are close to y naught of x. You can relate it to your one variable. Okay, when do we say that the function f of x attains the maximum at the point x naught? If f of x naught x minus f of x naught, this is less than or equal to 0. Okay, this quantity, I am not taking modulus and all. If this quantity is less than or equal to 0, then what do we say? That at the point x naught, the function f is having the maximum. Okay, and from where this x is chosen? This x is chosen from the neighborhood of this x naught. Okay, so in the neighborhood from close lying curves, if it is having the at the point x naught, if the function is having the greatest value, then it is called as the maximum. Okay, in that we call it as a local maxima. Okay, so just to get the idea of what it is, I have related it to one variable. Okay, and further to that, if suppose this delta v, it is having the value less than or equal to 0, and this delta v is equal to 0 only at y equal to y naught of x, then y equal to y naught of then it is said that at the curve y equal to y naught of x, a strict maximum is reached. Okay, so the condition is, if this is less than or equal to 0, then we say that at y naught of x, the functional vy of x is reaching the maximum. Okay, but if it is less than 0 and it is equal to 0 only at y naught, okay, then we say that at y naught v has a strict maximum. Okay, and in a similar way we can define the minimum. So what will be the change? There will be minimum here, and for all the close lying curves for around this y naught, okay, this will be greater than or equal to 0. And similarly, if it is equal to 0 and greater than or equal to 0, so at the point y naught, strict minimum will be achieved. Okay, so this is the meaning when we say vy of x reaches a maximum. Okay, now if you see here, when I said for the values of the function vy of x on any curve close to y equal to y naught. Okay, now in case of functionals, when I am saying close to y equal to y naught, what do I mean by close to y equal to y naught? We have defined the closeness in various ways. Yes, closeness in zeroth order proximity, first order, second order, okay, in general kth order proximity. Okay, so depending on this closeness, again there will be different natures of this maximum. Okay, like for example here, depending on this x, what do we have? Whether it's the local or the, we have local maximum minimum and overall maximum minimum of the function, right? And how does that depend? Depending on this x, if you are selecting only in small neighborhood this x, okay, if you are selecting in small neighborhood this x around the point x naught and you are checking the conditions, then you will get the local maxima minima. Yes, but so what I was saying is, if we have a function f of x and this f at x naught, okay, depending on where this x is varying, we call it as a local maxima minima or the overall maxima minima. Yes, so in a similar way, when we talk about the maximum and minimum here for the functional, it will differ by depending on from where or how we are choosing these y of x. Okay, because I have just said on any curve close to y equal to y naught of x. Okay, so what is this closeness, what order proximity? Depending on that, the nature of this maximum minimum will change. Okay, so they will be called as weak and strong. So let us now define So now let us define a weak extremum. Okay, so depending on from where these curves y of x are chosen, these curves, we will define a weak extremum. So a functional vy of x has a weak extremum for y equal to y naught of x if there exists delta epsilon greater than 0 such that this quantity has the same sign for all y of x in the domain of definition of the functional v, which satisfy the condition norm y minus y naught norm 1 less than epsilon. Okay, now what is the meaning of this? That means if this quantity is having the same sign means either it will be less than or equal to 0 or greater than or equal to 0. Okay, so if this quantity is having the same sign for all the y of x such that these y of x are, first of all, they are in the domain of the functional of v. Okay, and secondly, the norm 1 with y naught, that is y minus y naught norm 1 is less than epsilon. Okay, so for all the y of x curves which are satisfying these conditions, if this quantity has the same sign, then it is said that on the curve y naught of x, the functional vy of x attains the weak extremum. Okay, then accordingly now we will define the strong extremum. Strong extremum means what? If this quantity has the same sign for all the y of x which are satisfying this condition, that is they are belonging to the domain of definition of the functional v and they are satisfying norm 0, that is y minus y naught norm 0 less than epsilon. Okay, so if there exists the epsilon such that this condition is happening, and for all these y of x which are satisfying this condition, if this is having the same sign, then it is called strong, and if it is satisfying this condition, then it is called as weak extremum. Okay, so from here we can easily say that strong extremum, okay, this strong extremum will imply the weak extremum. Okay, so in order to understand this, let us first see what is this norm 1 and norm 2. Norm 1 means this is maximum of for all the x in the domain. Okay, the quantity y of x minus y naught of x plus maximum of for all x belonging to that interval ab y dash at x minus y naught dash at x. Okay, so norm 1 is defined as this plus this, and norm 0 is defined as maximum x, okay, y of x minus y naught of x. Okay, so now the claim is if at y equal to y naught, at y equal to y naught of x, suppose vy of x has a strong extremum. That means what? Vy naught of x is greater than or equal to vy of x for all the y of x such that it's a strong extremum. Okay, and I have considered a maximum. Okay, so what we want to say is strong extremum will imply the weak extremum. Okay, so let us take strong extremum, and extremum I will take it as a maximum. Okay, so Vy naught of x is greater than or equal to Vy of x for all the curves y of x satisfying norm. It's a strong maximum, no? So what will be the condition? They will be satisfying this norm. Okay. Now what does this tell you? For all y of x curves which are satisfying this norm, if we calculate Vy of x, that will be less than or equal to Vy naught of x, and therefore y naught of x is a strong maximum. But y naught of x will also be a weak extremum. Why? Because if suppose at some curve y of x, okay, it is having a weak extremum. That means what? If it is having a weak extremum, means this quantity is less than epsilon. Okay, when I say this quantity is less than epsilon, what do I mean? This is less than epsilon, this plus this. If this plus this is less than epsilon, is it true that this quantity is less than epsilon? Okay, so if at some curve y of x it is having a weak extremum, then that curve will be also there in this. Okay, here what we have considered? We have considered this quantity for all the y of x which are satisfying this condition. Okay, now if I say that at some y of x function is having a weak extremum, that means what? It will be satisfying this condition. Okay, so that y of x will be satisfying this condition. In return, what it will be satisfying? It will be satisfying that this quantity is less than epsilon. Okay, now this quantity is less than epsilon means what? Norm naught is less than epsilon, so that y of x will be also there in these y of x. Okay, and therefore it is true that if you have a strong extremum at y naught, then it will be also a weak extremum. Okay, and but if I talk reverse, that means if I have a weak extremum, then will it imply that it is a strong extremum? No, it will not imply always be true that if you have a weak extremum, then it will be a strong extremum. Why it will not be true? That is because, see here, if I say at the point y1 of on the curve y1 of x, I have a weak extremum. Weak extremum means what? Again I'll take the maximum. Okay, weak extremum means what? For all the curves, okay, for all the curves y of x which satisfy this norm, this quantity is having the same sign. Okay, now when I say that the curves y of x are satisfying this norm, what do I mean? I am considering the curves which are satisfying these conditions. Okay. Now, if I want to say that they will also satisfy norm 0 less than epsilon, all these curves, okay, that will be true. Okay, they will also satisfy norm 0, but there may be some y of x left out, okay, which is not satisfying this y1 norm, but it may satisfy this norm 0, and we won't be considering that y of x here. Okay, and therefore I cannot say that if it is having the weak extremum, it will have a strong extremum. Okay, I hope the concept is clear, because see here, when we are talking about the extremum, what are we actually talking about? We are talking about these values for all those curves y of x satisfying this condition. Okay, and here what I want to say is, for all the curves y of x which are satisfying this condition, we have claimed that it has a weak extremum. Okay, now we are checking that whether it will be a strong extremum. Okay, so for all those curves y of x which satisfy this condition, that means this condition, okay, they will definitely satisfy this condition, that is, this will also be less than epsilon. If this full quantity is less than epsilon, this will be also less than epsilon. Okay, so all those y of x will also satisfy this norm. But there may be some y of x which is left out such that it is satisfying this condition, okay, and not satisfying this condition. So whenever we considered all y of x satisfying this y of x was left out, no? But when we want to talk about the strong extremum, that y of x should be considered, and it will not be considered here. And therefore what we say is, strong implies weak, but weak need not imply the strong extremum. Okay, having seen the definitions of extremums, okay, or when we say that a functional is achieving a extremum on a curve y equal to y naught of x, okay, let us see what happens to the variation of the functional at y equal to y naught of x. If a functional vy of x having a variation achieves a maximum or minimum, that means the extremum, at y equal to y naught of x, where y of x is an interior point of the domain of definition of the functional, then at y equal to y naught of x, delta v is equal to 0. Okay, but what is delta v? Delta v is the variation, and this variation is equal to 0 at y naught of x. Okay, so if vy of x is a functional and it attains the extremum on the curve y naught of x, okay, then at y naught of x, the variation in the functional is equal to 0. Okay, and as I have already said that this variation, okay, it is given by with respect to alpha at alpha equal to 0. Okay, so this variation, it is given by this quantity. We have not actually seen the derivation of why this variation is given to be equal to this quantity. Okay, like if you want to relate this to one variable, what we say is, if at the point x naught, okay, the function is attaining the maximum, then what happens? F dash at x naught is equal to 0. Okay, so that is the condition, having the extremum, minimum or maximum, then f dash at x naught is equal to 0. So similarly you can remember it here. If the functional vy of x is attaining extremum at or on the curve y equal to y naught of x, then at y equal to y naught of x, variation is equal to 0. Variation in the functional is equal to 0. If you see here, if it is attaining the extremum, then the variation is equal to 0. Okay, and we will be using this condition to find out the expression which will help us in deriving the, meaning in finding this curve, that is the extremum curve.